All right. So question is, so we're talking about the classification. So we are trying to do, so far what we have learned is the solving problems with linear models, specifically using couple of techniques such as gradient descent. We also tried normal normal equation, and we also did various variations of gradient descent, and then we also learned how to use the same linear models to solve nonlinear problems by introducing polynomial variables. And then we also learned how to utilize the linear models in order to solve classification problems, right? Now, let's take a look at this diagram. What you see is here we have plotted the petal width and petal length. So petal length is on x-axis, petal width is on y-axis. So this we have done for few instances or few records, right? So this side, you can clearly see that petal length and petal width, it is this side. And the petal length and petal width, there is another one this side. The square one is versicolor, and the round one, the circle one, is setosa. Now, these two can clearly be separated with a straight line. These two can clearly be separated with a straight line. Now, out of these three lines, this, and this, which one do you think is the best one separating them? Yes? So all we're trying to do is, given petal width and petal length, we want to predict whether it's versicolor or it's setosa. Okay. So this is the training set that is given to us. And so we would like to draw a line so that we can tell in the future that which side of the line represents what, and hence that remains our model. So this is our model. This line that we are drawing is the machine learning model. And so it will be able to start predicting after a point of time when we don't have the, okay. All right. So yes, this one is definitely not, okay, but either of these are better than this model, correct? This one is not really separating anything. So this is a good model that if, let's say, this is the line, and if new instance comes here, then we'll be able to say that it is setosa, okay? So let me just draw it and give you more clarity on the. Okay, so let's say this is the line that we have drawn. Like the first one, this is first, this is second, and this is third, right? Okay, so these are the three lines that we decided to draw. And let's say the next data point is here. So this is, let's say, as per the first line, this is where this is setosa or versicolor, this one, as per the first line. Right, and okay. So as per the first model, Okay, while if you, let's say, draw here, right? Draw here, this is the second data point whose petal length is this and width is this much. So petal length is around 2.5 and petal width is around 0.5. So as per the first model, this one is, as per the first model, this one is correct. And as per the second model, this one is versicolor. Right, right. So basically, these are the model, these lines that we are drawing are the lines that are representative of the models. Great, great. Now, so, okay, so generally, when we are able to separate two classes with the single line, with the clean single line, or when we are able to draw a single line to separate the two classes, we call it the linear classification, right? So here we are able to, are we able to classify using the single line, the single straight line? Therefore, this is a linear classification. Okay, straight is a keyword here. It means linear classification. Okay, so here it's a, basically we are talking about the same data set. We have sepal length and petal length, and let's say we want to pick two features, sepal length and petal length, and then we have these three labels. Okay, so if you take a look at this data set, you will be able to look at it. Take a look at this data set, and this is how it looks like. There is sepal length, this petal length, and then flower type. While here we have drawn petal length and petal width. Okay, so 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 again, here is some more questions. So for the above iris data set, for this data set, what are we trying to achieve? This is our target. This is our sepal length or petal length. So quickly, is it regression or classification? No, we are trying to predict the flower type. We're trying to predict the flower type based on sepal length and petal length. Correct. So it's a classification. Now, what type of classification it is? What type of classification is this? Multi-class or binary? This is the target, and this is the data. Quickly. Right. This is multi-class. Okay. How many number of features quickly? This are we okay. How many number of features there? Correct. Two number of features. Right now, in this particular problem, this particular problem, okay, this part of the problem, so the number of features are two. Okay, and number of labels or number of classes, three. Correct. Correct. Okay. Wonderful. Wonderful. Now, when we plot two features on the graph and label it by color, the class can be divided by a straight line, and hence it's called a linear classification. Okay, so as part of the linear SVM classification, so SVM is another technique similar to the gradient descent. So SVM is a similar technique. So this one, no, or this one. So number of labels or number of classes actually. Okay, number of classes. So it has versicolor, setosa, and virginica. Okay, maybe there is no data point with respect to the third one, right? That's why. Okay, so basically this is the problem that we're trying to solve. Ah, I see, I see. Okay, so yes. So here there are just two labels, but this was the actual problem. So sepal length, petal length, and labels for this. Yes, go ahead, Noor. Okay, so yes, let me just change the title. Basically, I'll just use the class, okay, so as to avoid confusion because, all right, let me just fix this. Okay. Okay. A question from Noor is, can you tell the difference between the this one? Okay. So question is from Noor, what is the difference between multi-label and multi-class? Okay. Okay. So multi-class and multi-label are, as we studied earlier, there's a minor difference. In case we are classifying something into either of the three buckets, okay, either of the three buckets, then we call that multi-class, okay. If we are classifying something into multiple labels, we are putting multiple labels on it, then we call it multi-label classification, okay. So if we are classifying something into true and false kind of scenario, we call that binary. If we are classifying something into either of the three classes, A, B, C, or D, or one of the multiple classes, then we call it multi-class. If we are putting labels on something, there could be multiple labels on the same thing, we call that multi-label classification. All right? All right, so we're going to discuss good model versus bad model. And then we will talk about soft margin versus hard margin as part of SPM. Okay, then we'll talk about nonlinear stream regression. Okay, all right. So, okay, let me go back to, all right. Now, so here what we observe is, let's say we have an instance slightly here, okay? Right? So as per the model number one, as per the model number one, this one is versicolor or setosa. This one belongs to this or this. Quickly, as per the model number one. As per the model number one, for this petal length and this petal width, how it is going to be classified? It is going to be classified as setosa or it is going to be classified as versicolor. for this data point. Point is little above the line. Point is where the cross is. Okay. All right. Do you think it's right? Theoretically, it should have been as per our understanding, it should belong here. But because of this model, because of this line, which is very close to data points, it is actually being counted into this. Okay, does it make sense to you? So here what we have drawn is we have drawn a line, this line and this line. These lines are drawn such that they separate the data point and they are closer to our data set. Okay, so therefore there is a mistake. There is a mistake in these models. These models are not generalizing well, right? The imagine now my next question is, let's say there is a data point here. Okay, this data point that you see, as per the model number one, as per the model number one, this belongs to this or this as per this model. This belongs to Setosa because of this data point that you see. The cross is the one which represents the data point. So this one, because we are trying to draw the line very closer to the data sets, okay, therefore these are not generalizing so well, correct? So instead of trying to draw a line which from which the distance of both the data points are very less, okay, we need to draw the line which creates maximum margin between them. Okay, so same is true for this and so on, right? So basically we let here, okay, okay, so what you see here is these data points that you see here are supposed to be belonging to here naturally, right? While as per the model, this one belongs here and this one belongs here. Therefore, the way of drawing the line closest to the data point is not solving our problem. This is where this is where the the large margin, widest possible drawing a widest possible street makes more sense. Okay, so here you can see that these are very close to the instances here. That's why it's making mistakes and it's not generalizing well. While this side, if you instead of trying to draw the lines closer to the instances, try to draw a line which is far from both, which is equal distance from both. Okay, and yes, it can't be just far away in somewhere else. It needs to be between the data sets. Now, how to make that happen? If here we were trying to minimize the distance or minimize the loss, therefore we ended up with these kind of lines which are closer to the data set and did not generalize well. If we say that let the separating line be really far from each other, so the line could be here. Okay, And hence, again, it won't be able to solve any problem, right? Therefore, we need to draw a line like this. Okay, how will we make that happen? How can we make it happen such that we draw this kind of line, not this, not this? Is it clear? Okay, so these lines that we drew, they were based on we trying to minimize the distance from the separating line. Okay, we were trying to draw a line from which the distance of the data points is very less, as well as the as well as we were giving a as well as the data, the training set should be on the same side. Okay, so we should draw a line. If you were drawing a line such that these data points, they all come together on one side of the line, as well as the distance is minimum. Okay, but instead of doing that, we need to figure out something such that we can draw a line like this. If we say that let it be farthest, so this could be a model. Okay, but that doesn't solve a problem. Now, what we need to do is we need to instead draw a line such that there is a widest possible street between the two data sets. Okay, so we would try to maximize this gap, okay, and that's what is large margin of SVM classification. Okay, so we are going to try to maximize this street. We will try to make it wide as possible. Okay, so what we do is we draw a line such that the margin is maximum. Okay, so and here when the other thing is that as instances are added to this one, we will have to this model keep on changing all the time. One more instance, a training instance was added here, so the line has to be updated and so on. But in this case, the newer training instances may not affect the decision boundary. This is called the decision boundary. Okay, this is called the decision boundary. No, actually, this is called the decision boundary. This is called the support factors. Okay, this is called the decision boundary. So adding new training instances will not touch this kind of a line, because let's say we added one more training instance, one more training instance, and so on. It may not change this. Okay, while here, if the new training instance is going to be here or here, then we need to update the models. All right. So question from Noor is, how do we know if our model, which we generate in previous section, when pick or pick to? Okay. So here you will know that when you run this model on using, say, a cross validation, the chances of error are going to be very high. Okay. This model is going to give you bad output, either this or this. Both models, when you run them on cross-validation, they will give you wrong result. Okay, I mean the error will be too high. While if you have trained on the same data set and you're testing on the same data set, then you will be very happy because it has kind of memorized it and would be very happy to give you very good results. So this is where the testing and training separation would come. And okay, so this model looks very great if we have not selected the training and testing correctly. Okay, now coming back to here, the training instances may not affect the decision boundary in this case, while here it will keep on impacting it. Okay, so what are support vectors? Vectors are training data set located on the located on the closest to the classifier. So these data points that you see here, these data points are called support vectors. They are kind of on the side of the street, right? So here and here, these are on the side of street, extreme side of street. They are called support vectors. All right. So the living on the edge is the one which is basically has given the name as support vector machines. All right. So as part of SVM, what we do is we basically try to maximize this margin, okay, and as part of SVM classification. And these dots on the end, they are called the support vectors. All right. Now let me open the. Okay, are you able to open the notebook? This notebook is called support vector machines. Question from Inda is how to find support vector and define its boundary. We'll talk about it soon. Okay, let me just start. Okay, so here we go. Let's import matplot. Okay, now here we are. A question from Kamal is, can we not take few precautions and avoid the earlier approach to draw such erroneous decision boundaries? Yes, we can do that. Even with the normal regression that we have learned, we can do the same thing, okay? Just by selecting a proper cost function, okay? Just by selecting proper cost function, and you can actually get it done using the linear regression as well. But here, what we are trying to take is that the SVM classification can help in the nonlinear problems efficiently, as opposed to the linear problems. If a single straight line is not dividing something, and it's basically a curve that is dividing, so we will learn how to solve those problems. So the same problem would evolve into a problem where the data is separated by a curve. Okay, so in order to learn SVC, as in support vector classification, we are starting here. So your assumption is right, that it can we can actually do this kind of thing using the linear regression models. Okay, wonderful questions. Question from Pawan. For linear classification, if the point lies on the line, how we decide the class it belongs to? Yeah. So here, okay. Okay, yeah. So question is, do you mean here or here? Central line, right? If it is on central line, then you can't really decide. Okay, you can't really decide. And yeah, the chances of it being on both side is 50-50, right? And and remember our yesterday's discussion. If something is on that center line, one way to do is that if the probability is less than zero point 0.5, okay, probability is here we will be basically taking a very minor decision, and based on us say the way we decide yesterday, right? If the probability is lesser than lesser than zero point 0.5, let it be on the left hand side, or probability is greater than or equal to zero point 0.5, then on the right hand side. So that's how we will decide. Okay, so we'll compute the probability. If the probability is above, for whichever class it is above zero point 0.5 or equal to zero point 0.5, we will pick that. So yes, it would be an error and it won't be very right. Okay, and yes, good question, Pavan. All right, now let's just try to see if we could plot things. I think this is that petal length, petal width kind of model. So here what we have done is we have imported SVC from SVM. So SVM is a separate package. So earlier we talked about mostly linear one, okay, sklearn.linear, right? And now we are importing from SVM. We are importing SVC, which is part of SVM, and then we imported the dataset. Here we are loading the iris, which we have done it earlier also, and then we are just picking the second and third feature from the dataset, petal length and petal width, and then y is the target. Now here we are just saying we just want to keep two features for this example, okay? And here we are saying x equals, right? So we're just keeping these two features, and right. So the way we have done it is one, we have first generated true and false based on this condition for all the vectors, all the y's, and then we're basically picking only those rows where this condition was true. Okay, so that's what we're doing here, and so on. And then we are saying we are creating an instance of this algorithm as we see. Here right now we are just saying that consider it as linear, and we'll talk about C and the kernel, and then we are saying svm.fit. Okay, so right now we've just created this model svm, and it has generated this model. Now coming back to it, so we are trying to draw the same thing below. Keep in mind that here we've created a function called plot svc decision boundary, and what it does is it draws the decision boundaries. So this is the function which we are going to use again and again in order to draw these lines. Okay, so this part is being drawn by this. Okay, this part is drawn by this. Okay, these two lines and these dots are drawn by this function. Okay, that's what it does. It gets the decision boundary and then okay, and then draws it. Good. So this we have already talked. Okay, so hmm, right, right. Okay, so yes. So let me go through your questions. Question from Noor is, so in real world for classification problem, we should implement SVM, right? So question, yeah, so you are right, Noor. So based on past experience, it has been, we have seen that SVM generally performs better than most of the other approaches. But that doesn't stop us from trying out all other models. And in a data science problem or any machine learning problem, we must give a try to other models as well. But SVM, yes, definitely, it is proven to do a very good job in lesser amount of effort. uh, It is able to give better results. All right, great, great. All right. So both of you are right. Great. So now, what I want to discuss is that whenever we are doing this kind of a classification, the first thing we must do is we must make sure that we have standardized the data set. And who remembers what is standardization or scaling? Do you remember what is scaling? Okay. Now, what does it mean by scaling? How many of you remember? Correct. Similar units or similar range. That's right. Great, great. So let's take a look at this. Yes. So we are going to convert the data set between the extreme, between 0 and 1. So let's take a look at this data set. We have x1 feature and x2 feature and label it 0 and 1. Okay. And if we draw this, this is how it would look like. This is how it is going to look like. Okay. And okay. So if we take this model and draw the boundaries, and you can see that since this is unscaled, it looks really thin, right? This lane looks really thin. So instead, what we're going to do is we are going to scale the data set. Okay, we're going to do this scaling of the data set. A question from Bintao is, how does SVC work and how to choose the value of its parameters? Okay, that's what we're going to talk in this session. Okay, as a thumb rule, what we are trying again and again is we are trying to do things before learning them. Okay, we are trying to do things before learning them. Therefore, uh, we will go into more details as we keep on moving. So have you, all of you, opened this on CloudX Lab? Have you opened this on CloudX Lab? Abhinav, Balaji, Binta, Gigi, Kamal, Noor, Pavan, and Shahrukh. Great, great. So keep doing it. That's the only way to avoid sleeping in the class. The other way could have been that I could tell you jokes, but I'm pretty poor at it. So you'll have to keep tinkering while I discuss things. Okay, or keep asking questions. Otherwise, you'll feel sleepy in the class. All right. So this is where we are. So when the data set is unscaled, the lane, this lane that we are drawing, the street, is really thin. This is the decision boundaries are very narrow. Okay, so the first thing we need to do is we need to do the feature scaling. Okay, and for feature scaling, I'm just going to go really fast. A quick recap of what we've done. Feature scaling is basically converting things into into a certain fixed range. So there are two kinds of feature scaling. One is called min-max, other is called standardization. Min-max is basically dividing by max-min, something like this. Okay, so dividing by the total range, and subtracting each value with the minimum, and dividing by maximum minus minimum. Okay, the total range. So how far it is from the beginning, that's the one, that distance we are computing, and that distance we are dividing by the overall distance. That's what we are doing here. This is pretty simple. Now, the other one is standardization. Standardization is finding the standard deviation and then computing how many standard deviations each data point is away. Okay, so subtracting how many standard deviation each data point is away from the mean. So we subtract each data point with the average and then divided by the standard deviation. Okay, I hope all of you know what is standard deviation. Standard deviation is that right. Okay, so the standard deviation is what is the standard deviation? Standard deviation is finding finding what is the average value with which each data point is away from the center. Okay, so first of all, what we do is we first of all we find the mean. Okay, then we subtract the mean from each value, then we square each of them, we sum it up, and then we compute the square root of the sum and divide it by the total number of data points. Okay, so that's how we compute the standard deviation. And here further, we are subtracting each value by mean and then dividing by the standard value. Okay, so this is how we do the feature scaling. Okay. So min-max scaling is not very great, but generally on random data, you should prefer the standard scaler. Okay, now after scaling x1, x2, we would get something like this, something well within these values. Also note that in case of x1, the value hasn't gone to lesser than 1, right? Okay, it's a bit higher. So standard scaler does not necessarily forces data to be between 0 to 1, while our min-max scaling forces data to be between 0 and 1. Okay, so yes. So this is what kind of what kind of scaling are we using? Normalization, min-max normalization, or standardization? This is x new is x old minus m1 divided by s1. This is standardization. Okay. So here first we computed, let me just go back to the sheet here. See, we computed the mean, standard deviation, and so on. Now here we are looking at the standard scale features. Okay. So here the standard deviation S1 and S2 we computed. Now, what we are computing is X minus M1 divided by S1. So for each of these features, we have computed mean and standard deviation, and then we have done this. Okay. Now, question from Bintao is scaling the same as standardization? So scaling is a general strategy to scale the features, while standardization is one type of scaling. There are multiple kinds of scaling. One is normalization using min-max technique. Other is standardization using the standard deviation. Okay, so okay, yes, normalization and min-max is same thing. All right, did I answer your question, Binta? A question from Kamal. Standardization can still have a large range, specifically if few data points are far off the pattern. Right, right. So that's correct. So standardization still leaves the space for extreme large numbers, one or two extremely large numbers. But if you think about it, if you have huge numbers, okay, until the number is 1 in million, okay, the standardization is going to bring it down, okay, bring it down. Why? Because the standard deviation is going to be higher. Standard deviation is going to be really high, even if the one of them is deviating too much, okay, and therefore it will try to bring it down. Let's say few values are 1 to 3, and then there is 1 million. Still, the standard deviation is going to be around 3, not more than that. Okay, you could give it a shot. Okay, question from Noor. Standard scalar is a built-in function for standardizing? Yes. So that's a transformation provided by scikit-learn. Okay, so we could just say standard scalar, and we could say scalar.fit transform, and it will transform the data. Okay, the other thing is we could actually just add it in the pipeline the way we added earlier. All right, now after scaling, this is how the data looks. Okay, now this is a very important chart. Here, what you have is on the left-hand side, the unscaled data looks like this. While the same data, when we trained our models and we drew the decision boundary by using the SVM, this is how it looks. Okay, so which one do you think is better, this or this? Right hand side, correct? Because as I think Pavan was asking that what happens in case things are nearer to this line, right? When things are nearer to this line, there is more confusion. And hence, it's better to have bigger street with proper data points, with proper big thin is instead of thin, it should be a wider street, and hence less data points will be on the line, correct? All right, so this is why the SVM classification is specifically impacted by the scaling of your data. So do not forget to scale the data. Okay. So linear SVM is heavily sensitive to scaling. Okay. You could do either normalization or standardization, but standardization is generally considered more useful and proper. Scaled features produce better results for the above example. Okay. So let's just draw it and just take a look at it. Okay, this is where we have. So we're going to use the same function again and again to draw the decision boundary. Okay, this is the decision boundary. It's going to draw these dashed lines and so on. A question from Binda, is there a mathematical expression to SCM? SCM as in or SVM or SVC? Yes, there is quite a much maths involved in support vector machines. Okay, and we'll see if we could cover that in the class. Okay, there is quite a much mathematics involved in the way SVM does internally. Okay, and let me see if I could simplify and present it in simple words at a later point of time. Okay. All right, good. Now, the next question from Noor is expanding to Kamal's question. If there are outliers in the dataset, then standardization would reduce the importance of normal one. Yeah, try to do as much as possible, but still, there are high chances that one of the outliers or a couple of outliers could mm, could have really high standard deviation. Okay, wonderful, wonderful. So, okay, this is how it looks after scaling. Great, great. Now, Now let's understand the other terminology. One thing we understood was the standardization. The other part of the SVM is soft margin versus hard margin. Okay, so all we are trying to do is maximize the margin. Okay, now there could be two techniques under the SVM. One is called hard margin, another is called soft margin. So in case of hard margin, we strictly impose that all the instances should be off the street. Okay, and on particular side of the boundaries. Okay, so hard margin may not work in all circumstances. Okay, it may not it may not be able to draw the decision boundary, and therefore hard margin may not work always. Okay, so it strictly imposes that all the instances should be off the street. Okay, so question is if we want to draw a hard margin, okay, is it possible to classify this kind of data provided that there is one outlier? Yes, margin is the distance between the dotted line. Or the whole street is a margin. So yes, the dotted lines are the margin. Now, coming back to the point, so okay. So do you think it is possible to classify this using SVM hard margin? Yes or no? Correct. Correct. Pavan? Mintao? Okay. So the hard margin is that we don't tolerate. So it only works when the data is linearly separable. Okay, we strictly impose that all of the instances should be of the street, and all of the instances should be on the same side of the region boundary. Now, do you think it is possible to separate it quickly? All right, wonderful. So yes, it's not possible to classify this using SVM hard margin classification. Okay. But this kind of data we should be able to classify using the SVM hard margin. Okay. Hard margin as in it's a hard requirement that all of the data point must be on the same side, otherwise it won't work. So yes, it is possible to classify this kind of data, this is another data set where there is one particular outlier. Okay, it is possible to use SVM hard margin in this case, but what do you think is a problem? Quickly. Correct. The data points on the line. This street size is really small. The okay. So the this is the support vectors are really close to each other, and hence the model will not generalized well. Okay. So yes, the model will not generalize well. So because of hard margin classification, where we have the hard requirement of all of the data point must be on the same side, we ended up with a very narrow margin. Okay, we ended up with very narrow margin. So you can see that the trade-off here is between two things, keeping all the instances on the same side and the the size of the margin. Okay, yes, there is a parameter called hard margin in case of SVC. SVC is SVM classification. Now, the soft margin classification is keeping a balance between the two things, keeping the street as large as possible and limiting the margin violation. Okay, so instead of mandating that all of the instances must be on the same side, the soft margin classification does a trade-off, and the trade-off is between keeping the distance, keeping the street as large as possible, okay, and minimizing the margin violation, okay, and that's why there is a parameter called C. C is that regulatory parameter. If C is higher, the street is going to be narrow, and if C is lower, the street is going to be if C is narrow, the if C is smaller, the street is going to be wider. So more violation, more wider street, more violation, while the model is generally performing better, generalizing better if the street is larger. If street is narrower, the model may not perform great as we did in the beginning, but the model may the total number of violations will be lesser. Okay, so the trade-off between the violations, okay, violations means one instance which was supposed to be on the right hand side of the line is on the left hand side, or the vice versa. So that's called the violation. So here the C parameter, the regulatory C parameters duty is to regularize, to do the trade-off between the two. Again, C is a hyperparameter, so we could actually scan through the data set. Now, we could actually do the grid search, okay, with the C. Now, the balance can be, so if we have higher C, the street is going to be narrower, and there will be less margin, less violations. If the C is smaller, the street is going to be wider and more margin violations. Okay. A question from Noor is, so in this support vector, won't be one living on the edge? Okay, yeah. So there will be only those one data points, those extreme boundaries, they will be living on the edge. Okay. All right. But in case of soft margin, the chances of data points crossing the edge are possible. Okay. So here, let's take a look at this example. In the SVM classification for iris dataset using C equals 1, these are the steps that we are going to follow. The first one is load the iris dataset, model the SVM linear classification with the training set, and then test using a sample data. Okay, we are going to plot the decision boundary and training samples. So question to all of you is, did we miss any of the steps? Anybody? In this approach of machine learning, did we miss any step in these 3 steps? We just performed 3 steps. Did we miss anything? Quickly? Yes. So we actually missed the feature scaling. So we need to do the feature scaling. Okay, keep this in mind whenever you're performing your steps. And all right, so here we go. Let's just so here what we are trying to do is we're going to demonstrate the soft margin classification for same iris data by regulating C parameter. So this is where here in this case the SVM was impossible, so it could not draw the decision boundary. While in this case the SVM was possible, but the street was really narrow. The hard, as in with the hard boundary was not possible. Here, the hard boundary was possible. Okay. Now, for the same data set as previous, we are going to regulate C parameters. So we are importing data set, we are importing linear SVC, standard scalar, creating a pipeline. So in this case, it instead of giving error, it did not generate any boundary. Okay. So here on the left hand side, so we created this data set, right? And then we said linear. And since we are using C as really high, that means it's a hard margin. Okay. So yes. And then we try to plot it. All right. Let me just go up. Yeah. Okay. No, actually, we have not done the hard margin classification here on this side. Okay. So the point is that we are trying to, okay, we have not tried the hard margin actually. We did not compute the hard margin. Okay. So never mind. So basically, practice, we hardly ever use hard margin. We mostly use soft margin. And in case we really need to use hard margin, what we do is we bring down C close to the zero. Okay, we bring down C close to zero. And okay, all right. A question from Noor. So in case of LHS pig, will it give error? Yes. And question from Binta is, what are concatenate and annotate? Work in np.concatenate and annotate. Which side, which part is it? Let me just see. Concatenate. Okay. So we are just adding the outliers into the data set. Okay. We are just adding the outliers into the data set. So we're basically concatenating the data, and annotating means we are putting these various labels on the chart. Okay, that's what is annotate. All right, this drawing an arrow and all of this is part of the annotating. Okay, so that's what it is. All right. A question from Gigi is that why can't we skew the outlier? So in a way, soft margins does the same thing. Okay, let the outlier be there. Okay, that will be kind of ignored, or will be basically that will be the error in the overall model. Okay. Okay, now let's try to go through the SVM classification. And okay, so what we have done here is we have loaded the data set, we have picked up only 2 features, and here we are generating only for one class. Okay, generating for only one class, making it a binary classification. And then what we are saying is we're creating a pipeline. In this pipeline, we are passing a scalar, and we're passing the linear SVC model. This scalar and the linear SVC model. And then once we have the pipeline ready, then so pipeline is basically a tuple of tuples, okay, in which there is the name that we pass, and then the object of the particular transformation or transformer, we pass it here, and then we fit. Good. So this is what we get, and once we predict it, it is able to classify. Okay. All right. Now, okay. So, all right. So we loaded the iris data. This is what we did in the notebook. Then we did the scaling. Then we did the scaling, and then we did the scaling and modeling of the two by using the scalar, and then we tested using the sample data. And then we are going to plot the decision boundary along with the training data and so on. Okay. So this is the part, this function that we created earlier. We're going to use that function to plot the decision boundary and the other details. So okay, so this is where we have plotted the data. So what you see here is, in case of soft margin, there are outliers. You see that the triangles have come this side. Okay. Also, these ones are doing the violation. Okay, these ones are doing the violation because they're also kind of coming into beyond the decision bound. They are coming into the street. Okay, so there are so many violations. Okay. All right. So you can see that as we increase or decrease C in our model, so the same thing what we have done here. Here we have passed C as 1, but when we pass C as 100, the graph is different. So when we plot the entire graph between the petal width and petal length, and then try to separate them with a street using the soft margin, this is how it looks. If this regularization parameter is really high, this street is going to be narrow. If the regularization parameter is low, this street is going to be wider. This street is going to be wider. You can see that? So when you have C smaller, the chance of error grows. The number of errors keep on growing as C keeps on going down. As C keeps on increasing, the errors keep on decreasing. Is it clear to everyone? So standard scalar, we are using that scalar here question from Vinta. Which scalar are we using? Let me just show you. We are using standard scalar. Okay, not normalization. We are using the one with standard deviation. Okay. Right. If the C is higher and higher, the the errors are lower and lower, and therefore it will kind of convert it into hard margin. That's right. Instead of, I think I said it C at 0. So yeah, C, if C is higher, then it will convert into more into hard margin because total number of errors will keep on reducing. Okay. Yes, you're right. Okay. A question is, what is the good value of C? Here we are able to look at the visualization. So generally, the good and bad is a function of how well. So good and bad is a function of how should I say? So the objective is to achieve minimum number of errors, and that too on the training, on the using the cross validation, right? So it's a very good question and very important question, that how do I know what is right? Correct. So when the street is narrow, we are able to get very good results on the training data set. But on the test data set, if the street is narrow, very thin street, the chance of error keeps on increasing. Okay. So if the street is wider, the model keeps on improving. Okay. So therefore, there is always a trade-off with C, and hence you leave it to generally the grid search or the cross validation to figure this out. So we try all various values of C. So the way we do is we take a value of C between, say, very small to very large, and do a coarse search first. Remember that random search in the grid search, where grid random search, whereby what we were doing is randomly picking between very extreme, and then doing that. So first you do the coarse search to find the value of C, and then do the fine-grained search. The range should, for the next one, would be smaller, and hence the result is going to be better. So first you do the coarse search, then you do the fine search to find the hyperparameter C. Okay, there is no single way of doing it. Okay, a question from Bintao is, how does SVM1, let me just take a look at the code. SVM underscore CLF 1 dot capital C. Is that the one you're talking about? Which one are we talking about? Yeah, this one, right? So basically here, this is the C that we are passing. Okay, and let me go up. I'll show you that at the point where we are creating this object, we would be passing the C. Okay, so we are passing the same value of C and accessing it here. Okay, accessing it wherever we want to plot it. Right? So no, all right. So here we will be basically accessing the same one. So this is something which we specified above while we were creating the objects of SVM CLF1 and CLF2. This is where we created the two objects. Good, very good questions. So moving ahead. Now, so next question is, what is the model we used here? SVC, SGD, or linear SVC? Anybody? You'll notice that these two are SVC and linear SVC are two different things. Okay, though this one says kernel equals linear, and these two are actually two different algorithms under the hood. Okay, so here we're using the linear SVC. All right. All right, so that was a quick understanding of what is soft margin, hard margin. So we have so far used linear SVC. Okay, keep that in mind. Now let's try to understand the nonlinear SVM classification. Right now we are assuming that the algorithm exists, an algorithm works. We are just trying to understand the various use cases and various circumstances in which the SVM would be used. Okay, and what kind of fine tuning would be required. Okay, so right. So now, so far, it was possible to separate the data using the straight line. Therefore, we were able to use the linear SVM or linear SVC. Now, many data sets are not linearly separable, meaning many data sets cannot be separated. The many features cannot be separated by a straight line. So the first approach is to add more polynomial features. The way we did earlier in case of linear models, what we did was we added more polynomial features. Okay, and that could result in linearly separable data sets. Let's take a look at it. Now, imagine that we have two classes, square and the triangles. Okay, square and triangles. For some feature x1 and some feature x2, this is how it looks like. So, okay, so this is x2 and this is x1, and this is how the data set look like. Can you separate it with the linear line? Can you separate triangles and squares with a straight line? Yes or no? Is this linearly separable? Correct. It's not. It's not separable by using a straight line. Correct? Balaji, Bintao, Gigi, Kamal, Noor, Pawan. So are you still there, or have I put you to sleep? Okay. So it's not linearly separable. We can't separate squares and triangles in this diagram by a straight line. Therefore, let's try to square values of x1. Let's try to square it, meaning -4 will become 16. This will become something like 9. This will become 4. This will become and so on, right? While the y will remain as such, the x2 will remain as such. So what we get as a data set is 16, 9, 4, 1, 0, 1, 4, 9, 6. Okay, so this is how it would look like. So the x1, though the feature x1 remains as such, the yth, so the second feature x2 has become very prominent. So between x1 and x2, if we draw the plot, this is how it is going to look like. Okay. Now, since it was not possible to separate the data points using just one feature plus maybe some other feature, but if you square it, suddenly it is possible to separate the triangles and squares. Okay. Is it clear to all? So by adding polynomial features, such as here, what we added was we added one more column x2 and squared the data in x1. Now you can see that both x1 and x2 are now separable by using the same straight line, using a straight line. All right. Quickly, is it linearly separable now? Right. So right, this is what we have done in this diagram. Try doing that. Now question is, so there is a data set called Moon's data set. It's basically a random data set generator provided by Scikit library. It has two dimensionals, or you can say that it has two features, single label, and it is generally used for binary classification. Okay, so we can generally use this function called make moons, and it will generate the data. We can pass the number of samples. We could tell how much noise we want, and we could also provide a seed so that every time we run it, we should get the normal results. Okay, this we have done it for our own purposes so that it becomes easier to explain. Okay, now so what we have here is we have two features, x1 and x2. When we plot it, this is how it looks like. So this one is class 1, class 2. Now, so this is the randomly generated data. Okay. If we generate hundreds similar data set and plot them, this is how it is going to look like. Okay. Is it linearly separable? Yes or no? So we've just generated some random data in order to, okay, so we have make moons, and right now we're just passing. Okay. Now, question to all of you is that how to classify this using linear classification or using linear classifier. Anybody? Okay. Okay. So Noor's suggestion is we add polynomial features to it. Good. All right. So should we take a break for 10 minutes? Okay, let's take a break for 10 minutes and we'll be back in. So should we start? I'm back. Should we start? All right. So question is how to classify this using linear classifier. One of the suggestions was from Noor that to add polynomial features. Any other suggestions do you have? All right. So let's try to add polynomial features and then see if it is working or not. Okay. So if we add a degree 2 polynomial, if let's say your data is x1, x2, and label is 0 and 1, 1 and 0, then say we add a degree 2. Degree 2 means x1 square, x1 into x2, and x2 square. Okay. These are the 3 extra columns that we are going to add. Okay. So let's see if it works. So here we are saying that first of all, we are creating data set, then right, then set print options, I mean some print options to display on the UI. Okay, so this is what we are doing there. Yeah. Okay, so first of all, we created some random data. Then we did the pipeline for polynomial classification. Okay, first of all, we are adding polynomial features. Then we are adding a scalar, because if we added, we could do the scaling after also, but then the say 0.1 square will become 0.001, right? Therefore, it's better to scale after adding the polynomial features. Now, the then we are calling linear SVC. Okay, and then we're calling polynomial SVM fit. So what you see here is then, and then finally we are plotting the predictions. Okay, so this is how it looks like. Okay, so this is what it has done. You can see that it has been able to kind of separate the two data points, though it has been able to classify the data set, though there are outliers. You can see the triangle is here, there is another triangle, and so on. Okay, so basically it is able to kind of classify. Okay, now what if we add features with the degree 3? Okay, let's see what did we do just now here. Okay, so we are saying loss is hinge. Okay, that's a separate thing we'll talk about. And then let's say the samples are this. Here actually degree is 3. That's what we have done instead of degree 2. Okay, so we are using a 3-degree polynomial. Now question from Intao is, how does make moons work? How does make moons work? Make moons is basically random sample generator. I'll just show you. Okay, I'll just show you. You can see that it is basically generating 2-column data with 100 as samples. I think there will be 100 records like this and so on. So make moons is that. Make moons is pretty simple, straightforward tool. Okay. Question is, how do we decide degree of polynomial? Again, the simple answer is cross-validation by basically figuring out whether we are overfitting or underfitting. Okay, so the philosophy remains same as we discussed earlier, that if we increase the degree of polynomial, we'll start overfitting and memorizing, and if we decrease it, then we might underfit. So the simple answer is using the cross validation. All right. So here the loss is hinge. Loss hinge means basically using the basically using the, what do you say, linear one, L1, not instead of L2. Okay. So yeah, we will look into this again. So because loss, hinge loss, we used earlier also, and we used in terms of the thing. So we'll just keep it aside for now, and yeah, we'll go into details as we go ahead. Okay. All right. Wonderful. Wonderful. So yeah, we'll come back to the loss equals hinge later. Okay. The hinge loss is the loss function that we had discussed earlier. Also, I'll take you back there. Okay. So let's try. Let me just cough. Good. So let's take a look at it. So what we have done is we have been able to classify. Okay. So what we just saw was that with the polynomial features of degree 3, we were able to do a non-linear classification using the linear classifier, and using the linear SVC, we were able to separate the data which is randomly generated, and there is a curve. Okay. Now, all right. So now, so we generally call something the kernel. There is a term that we use again and again in the support vectors is kernel. What is kernel? Kernel is essentially the center of it, and the kernel is okay. And we'll talk about. So let me just explain. So when we have complex data set, one technique that we used was adding polynomial features. Adding polynomial features. So we added we said that generate the data set by squaring it and multiplying the two data points, and third one we added by squaring it. So basically, by introducing the polynomial features, we were able to classify our data. Okay, classify our data. Now, the so while on one hand the low degree polynomial, the polynomial features with low degree cannot handle complex data, while on the other hand the high degree polynomial features make the model slow due to huge number of features. Correct? Because if we say degree 3, then it'll become x cube, x square, I'm sorry, x1 cube, x1 square, and then x1 into x1 into y1, x1 into y square, and so on. So then y square, y cube, and so on. So as we increase the degree, the total number of features start exploding. The total number of features start increasing hugely. Therefore, the overall process would become really slow. Okay, so on one hand we can't use the linear SVC on complex data. On the other hand, the polynomial features, the polynomial degree makes the process slow. So there is something called kernel trick or polynomial kernels. Okay, so there is something called kernel trick that again we will describe it in detail later if the time permits. So the kernel trick is something that SVM provide in order to make it possible to give you the very good result using the low polynomial degree. Okay, so without having to add so many features, without adding so many features, we can achieve the same result as the high degree polynomial, even better than that. So this is a feature provided by SVM, and we call it the kernel trick. Okay. So, so all we have to do is, instead of saying kernel is linear, we say poly. And instead of using linear SVC, we'll use the SVC with kernel equals poly. Okay. So that's the difference between the two. If you go back here, so what we have done here is we have defined the linear SVC with these hyperparameters, right? Now, in case of the kernel, what we do is we say that we are instantiating SVC with kernel equals poly, and the coefficient is 1. So basically, okay, so yes, so basically, I have not described kernel much. All I've described is that the polynomial features kind of slow down the entire data set, because as you increase degree, the number of features increase exponentially, right? Uh, And okay, so we have for these situations, we have something called a kernel trick provided by SVC. Okay, so all we are doing is we are calling SVC with kernel equals poly, and here we are specifying degree equals 3. Okay, so we don't need to go beyond too many new polynomial features, and this would be able to do the job. There is a hyperparameter called coefficient 0. It controls how much model is influenced by high degree polynomials versus low degree polynomials. Okay. Okay. A question from Bintao is, there are so many packages within sklearn, and how many of them do we have to know better, do we have better know about? So whatever we are discussing in the class, that is actually more than enough. Okay. And the depth also we are taking care of. All right. So don't worry about this part. So, so this coefficient 0 is essentially controlling that how much model should be influenced by high degree polynomials as compared to the low degree polynomials. Okay, so basically here what we have is we are trying to, also we have the c equals to 5, which is basically saying that how much do we want to, how big do we want the lane to be, the street to be, and so so here we are calling that, and now you can see this, that this is coefficient 0, r equals 1, and this is coefficient, this is same thing. So you can see that I'll talk about this coefficient 0 a little bit more in details. Okay, so what we have is, as the x1, okay, is increased, these are two features, x1 and x2. This is in one class, this is another class, and here this is what is generated for d equals 3, as in the polynomial degree is 3, the coefficient is 1, and the street is 5. Now we increase the number of degrees. We said it's 10, and the r, the coefficient is 100. Okay, and the c equals 5, how much do we want to tolerate crossing the border or crossing the distant boundary? Okay, so that's what is the c. And so you can see that here in this case it is more round, and basically trying as much precision as possible. Say for example here, it it kind of let this be on the other side, while on here it has gone through that. Okay, so So basically, as R increases, it and degree increases, it basically tries to be nearer the data as much as possible. Try to consider every data point. So here it's trying to definitely overfit. It's trying to definitely overfit, but at the same time, it is um, as the I'll talk about this part soon. What does it mean by coefficient? So okay. So this is basically a regularizing parameter. R is a regularizing parameter which controls how much our model should value the low degree, higher degrees as compared to the lower degrees. Okay. So this is what is the outcome. We'll discuss it in more details. Okay. All right. It's the same thing that we have just discussed. Okay. All right. So when the you can see that when the degree is smaller, okay, when the degree is smaller, the curve is round. It has let go of some of the data points like this one, but this is more rounded and so on. As the degree increases, what it is doing is it is trying to touch every data point. It is trying to touch every data point, and kind of like here there is one outlier, here there is one outlier, here it has tried to consume that as well. Okay, so I hope this is clear to you, the difference between low degree and higher degree. And all we have done is the we have introduced something called kernel as polynomial. Okay, kernel as polynomial. In both the cases, both are polynomial kernel. So there's not much of a difference between lower degree and higher degree. That is first observation. Okay, so even the lower degree is giving us good enough result, right? You can see that clearly. And and therefore the kernel trick, even with the lower degree, solves the problem, right? What if we put the degree here as 2? Okay, if degree is 2, this is how it looks like. Okay, this is how it looks like. Therefore, degree equals to 3 does make sense. All right. Okay. So question is the let me go up. Okay. So when we are adding the when we are doing the where is the yeah. Okay. All right. So what's the difference between these two? The main difference between these two is one is without using the kernel, without using the kernel. Other is with using the kernel as poly. So this one is far more efficient than the previous one. That's the main difference. This one will be faster and more efficient. All right. So basically, we use the two techniques. One is using a linear SVC with polynomial features. Other is using the kernel equals to poly, and that also did the same thing. Okay. that also did the same thing. And just that this technique, kernel equals to poly, is far more efficient, makes the entire process far more efficient as compared to the polynomial features. That's the main difference between the two. All right. Good question. So, all right, was he able to answer your question, Noor? The main difference between kernel equals poly with SVC versus the linear SVC, the main difference was with respect to the time it takes to compute. Okay, so though we have not been able to demonstrate it here, but in practice, the as you increase the number of features, you will end up with with a lot of time and memory consumption. Okay, so overall, overall, the kernel equals to poly is something that helps a lot, and in most of the classification, in most of the linear classification, we generally end up using SVM with the kernel trick. All right. Now, the other part that some of the parts that we would like to understand is okay, a question from Bintao is what is R before this? Okay, so R is essentially, okay, in the title, right? I think it's a color or something here while plotting, right? Okay. Generally R we used for regex, and I don't know what it is being used. Okay, from here to here. Okay, so R means raw string. Thank you, Kamal. R means raw string from here to here, so that it should not be treated by anything. Okay, so it'll take this here and then basically do the substitution and others. Okay, so basically this part is for title. Thank you, Binta, for the question. Okay, and this R is actually that coefficient 0, which controls the lower degree polynomial influence versus the higher degree. Okay, good, good, wonderful. So there are a few more concepts in the SVM, and so keep trying whatever is there in the notebook. Okay, so another technique of solving non-linear classification is add features computed using similarity function. Okay, so let me take a step back. Now, what we learned earlier was that we could add the polynomial features, right, by x1 square, x2 square, and so on. So that is one technique. Okay, the other technique is to compute or add new features which are derived from existing columns. Okay, and how? Based on something called similarity function. Okay, based on something called similarity function. So similarity function here is very simplistic. So all we do is for each data point, what we can do is we compute the distance from a landmark and create a new column. Okay, so similarity function measures how each instance resembles a particular landmark. Okay, how each instance resembles a particular landmark. Say for example, this one is impossible to separate using linear classification, right? We can't separate it with a single line. Now, let's say we introduce a landmark called X. Okay, so this is our data set. It has -4, -3, -2, 1, 0, 1, 2, 3, and 4. Okay, -1 belongs to the different class, 0 belongs to different class, -1, 0, and 2 belong to the same class, while rest belong to a different class. So what we do is a question from Binta: how to check sklearn with help within the Jupyter notebook. Okay, so you can generally, let me just answer this question. Okay, so let's say we are, okay, first of all, you'll have to import it. All right, you'll have to say, let's say, import sklearn, okay, and then say help sklearn. All right. Similarly, whatever you import from sklearn, then that you can do. Okay. So you'll have to import SVC. Okay, not SVC, we'll say. We'll have to say from this, it's a, yeah, sklearn.svm is a package and SVC is a module. So we'll have to import it like this. Okay, so this is how you could do that. Is it clear? But you'll have to import that, either the package or the module. Either you import this. All right. Great. So what we're talking about, we are talking about deriving new features. One way of deriving new features by using the polynomial way. The other way is something called, something based on the landmark. We call them similarity features. Okay. So let's take a look at the landmark one. It's a very important concept, so please pay attention. So here what we are trying to do is, for here, we'll just choose a particular landmark, subtract the distance from it, and then create a new similarity feature. So, and this similarity feature is based on this kind of a formula. Okay, this kind of a formula. All right. So what we do is this is again a hyperparameter. This gamma is a hyperparameter. So let's say gamma is something, and this is the distance of each point from a landmark. So let's say we choose this as a landmark. Okay, so the distance for this, okay, this is square, therefore e to the power square, and hence this is far smaller, and the distance of this one is 0, 0, and therefore e to the power 0 is 1, therefore this is maximum. Because you see the minus sign here. So the ones that have far more distance from this are going to be having a smaller value. And this here we are putting in exponential. So what we are saying is things which are distant from a landmark, they will be having smaller value. The things that are closer to the landmark, they will be having this bigger value. So essentially, the data points which are similar to the landmark are going to be bigger. Data points which are not similar to the landmark, they're going to be smaller. All right. So we basically are adding the landmark. So the more landmark we'll add, the more features we generate. So for each feature, for each landmark, a new feature will be created. Okay, a new whole column will be created. So basically, this is how we are adding more features which are called similarity feature. Here, the similarity is based on the distance. Okay, and to emphasize the distance, we are using exponential. This is 2.3 to the power this. Okay, the other thing is negative. So this negative is to make sure that the values which are far away from the landmark, they are smaller, as compared to the ones that are closer. Okay, so you can think of it as negative of the distance, and that's fine. Okay, is it clear to everybody? So what we are doing is we are generating new features from x1. Right now we had only these x1 feature with these 1, -4, -3, -2, -1, 0, 1, 2, 3, and 4. This was our data set x1. Now let's say we chose two landmark x2 and so this and this. So new data set would be with respect to -4, this will be somewhere here. With respect to -3, this will be somewhere here, here, and so on. So based on these values, we are creating the new features. Okay, looks complex. So instead of just squaring x1's value and adding more polynomial features, here we are finding the distance of x1 from a landmark and then emphasizing its values. Okay, emphasizing its values meaning we are doing the e to the power that value. Okay, we are raising each distance. We are raising e with the distance as the power of it. Okay. Question is, what is x? X is this. Okay, x is the whole vector representing all of these data points. Good question. Again, question from good question. Question from Binta. How to choose the values of gamma and I respectively? So here there are two things that we need to choose: L and gamma, right? So how, that's a question from Binta. How do we choose these? Okay. Again, there is no straight rule. So the way we choose L is basically we make every point as the landmark. We make every point as the landmark. Okay, and if there are 100 records, then there will be 100 new features. So that's one way. The other question from Kamal, is it e to the power everything in brackets? That's right, e to the power everything in the brackets. Okay, and this essentially means mod or absolute, you can say. This not basically it's absolute, or you can call it L2. Okay, this is Euclidean distance, we call it. Yes, go ahead, Noor. Yes. So right now we have, now question is, right now we have added two landmarks, this and this. These two landmarks are arbitrary, correct? Correct. There is no need to write the modulus because we are already squaring. Okay, we are already squaring. You're right. Okay. So question from Noor is, you said we make every feature landmark. Yes. So right now we are just adding two landmarks, but in practice what we do is we add one landmark with respect to each data point. So number of features, if there are m number of instances, the number of features are also added as m. If there are 3000 features, 3000 records, the 3000 features will be added. Okay. So basically for every record, there'll be a one landmark for this, one landmark for this, one landmark for this, one landmark for this, and so on, right? And therefore, with respect to -4, we'll compute one x2. With respect to this, we'll compute x3. This we'll compute x4, then x5, and x6, and x7, and so on. Okay, question from Kamal, why so many new features? How does it help? Okay, it helps us in solving really complex problems. So here if you see that here these data points are inseparable, correct? these data points are inseparable, but the moment we generate this feature, say x2, suddenly the things will become separable. Okay, so similarly, as we do this with all other data points, the data points will be more separable. Okay, a question from Noor. So with each landmark, we calculate features for that landmark only and not all the features. Then why we have, yes. So what we do is here what we are doing is we are computing, let's say for this, we will compute all the instances for that feature. Okay, so let's say our distance is from here. So first we'll compute the distance of this from here. Okay, just like we did for this one. So that is a better example. So the way we took this is our landmark, and we computed a new feature. How did we compute? By applying this formula on every value, by computing the distance of this from this, and then raising it to the power e. Okay, then we get this value, then we move ahead, and then we get this value, then we move ahead, then we get this value, we move ahead, we get this value, then we move ahead, we get this value. So for all of the data points, this is what we are going to do. For all of the data points, we are going to generate new values. Okay, so per landmark there will be a new feature created. Okay, question from Binta, is similarity the same? Yes, so similarity here means the distance. Okay, the less the distance, so basically this phi that you see here, this is what we call similarity feature. Okay, this phi represents similarity, meaning if something is closer to this, the similarity is going to be 1. If something is far from it, the similarity is going to be lower, like here. Question from Noor is, question from Noor is, for one landmark in dataset, we will have m-1 new features. Correct. Yes. So no. For one landmark in the dataset, we will have one more feature with m-1 more values. Actually, m new values. Okay. M is not number of features. It is basically the total number of instances. Okay. So here x1 is one feature. Let's say there was only x1. Okay. And how many data sets are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say 9 data points are there. 9 instances are there. So there is one feature, 9 instances. Now we have just introduced two landmarks. Therefore, 2 new features were created. Okay. If we consider every data points, okay, every data points as the landmark, then there will be 9 new features. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 new features, one for this, other for this, and so on. Okay. Did it make sense to you? Kamal? Balaji? Okay, so we basically are using this formula to just change one column into another. I think this will be a better example. Say we have x1, -4, -3, -2, -1, and 0, 1, 2, 3. This is our original data set. Okay, this is a feature called x0, and the label is this. Okay, now we are say computing x2 based on the landmark 1. Landmark 1 is say -2. Now the distance is -2, -4, and say gamma is 0.3. Okay, gamma is 0.3. That is the coefficient hyperparameters. So we are basically creating more number of features. All right. Question is from Kamal. But with this step, number of features will become larger than number of data points. That's right. That's right. Okay. Right. Uh, in our past discussion, the okay. So question from in our past discussion, we had the uh, discussion about can there be a situation where the number of features are more than number of records? Can there be a situation where number of features are more than number of instances? This is clearly the case. Yeah. Question from Noor is how many landmarks to select and what would be the criteria? Good question. The general strategy is whatever is there in the X1, your feature, make all of these as landmarks. Therefore, if it has 9 records, there'll be 9 more columns. Okay. Now, once we have generated the new data points, okay, so these were our older points. Once we generated new ones with using the similarity. So these are similar functions, similar features to the actual one. And you can see that you can clearly separate them. You can clearly separate them. All right. Yes, X would actually be a vector, not a point. Wonderful, wonderful. So let's try to add the similarity functions using this and take a look at whether it works or not. Okay. Okay. So I think this we have already answered. This question was from Noor. Question is, how do we select landmarks? Create landmark for each and every instance in the dataset. If the training set is huge, number of features will be added, will be a huge number of features will be added. So this trick is great if you have a smaller dataset and you want more precision and you want the clarity. A question from Abhinav, if we choose as many landmark as features, the number of features and number of data points will be same. So there'll be, so question was here, okay, so here, right? So we had X naught, correct? We had X naught, and let's say it has 9 features. So one, we'll make this as landmark, and that will create one more column. Then we'll create one more column for this, and so on. So the number of features will become 10, while the number of records will remain 9. Okay. So here, number of features is one more than the number of data points. Good, good. Wonderful. Now, the okay, so the same thing is shown here. Okay. Now, in this case, how many data points will be added? Quickly. How many features, sorry, not data point, how many features would be added to this? Ignore this part, ignore this part. So whatever we've discussed just now, okay, let me fix it. So that's right. 9 more features will be added to this. I'll just delete this portion. Okay. Now imagine doing this with huge training sets. Okay. If we have huge training set, it is going to consume a it's going to consume a lot of memory as well as a lot of CPU cycles. Now now this is where the nonlinear SVM classification comes into play with something called Gaussian RBF kernel. Okay, so the similar to what kernel trick we had earlier, right? So polynomial feature addition becomes slow with higher degrees, and kernel trick solves it. Similarity feature becomes slow with higher number of training data set, and this is where SVM kernel trick again makes it faster and thus solves the problem. Okay, so great. So it let us go to similar results as if, so there is something called Gaussian RBF kernel trick. Okay, okay, so we call it SVM kernel trick again, and then what it does is it lets us to get similar results if we had added many similarity features. So Gaussian RBF kernel lets us to get similar results if we had added many similarity features without actually having to add them. Okay. So the similar kind of impact SVM Gaussian RBF kernel brings as adding many similarity features. Okay. So this is how we use the SVC kernel with SVC with RBF kernel. Okay. So this way. Now let me go back here. Yeah, correct. So right. So this is how we use the RBF kernel trick. And all we have to do is first of all do the scaling and then call SVC with kernel equals RBF, and gamma is 5. Gamma is same as this gamma that we had here in this formula. This is that gamma. Okay, this is that gamma, and here again this is that it's the same C that we discussed in the beginning. Okay. All right. The RBF, I think, is named after the 3 researchers who worked on this one. Okay. So, all right. All right. So RBF is after the 3 researchers, as per my understanding. I'm not really sure about the full form. Yeah. No, I doubt it was there. Just let me go back. Okay. Okay, let me just go through it. Is it the radial basis function or something? RBF. Yeah. Yeah, it's a radial basis function. Okay, so yes, you're right. Good, good. All right. So basically, let's take a look at RBF kernels after plotting it. So what you have here is the okay now if you see if the here if gamma is 0.1, then this is how it looks like. If the gamma grows, then okay, then it looks like this. Now, okay. Now, if the C is this much, 0.001, if C is this one, then the C is very small. That means it is okay to let it be, let the boundary, let the elements cross the boundary, as in the boundary could be smaller. The distance or the support vectors could be smaller, and as the C grows bigger, okay, C grows bigger, the tolerance grows lesser, and hence this is how it looks like. Okay, so for the same gamma, if we have this. Next is if we just increase gamma from 0.1 to 5, what happens is when if you take a look at the similarity functions, okay, if you take a look at this similarity function called gamma, what happens is if you increase the gamma, this suddenly the second feature which are being derived from here, they'll become far away from the actual data, and therefore it will be easier to separate them. Okay, so you can see that just by increasing gamma, we are able to separate the data, okay, while the C remains same. Further, we are adding C equals 1000, and hence the distance will be higher, and so on. Okay, the tolerance will be lower. If you have C as higher, the tolerance will be lower. And such as this outlier is there, so it could not, here, it has separated that outlier also. Okay, so you can see that as we increase gamma, the emphasis on each of the function is each of the feature is increasing, and hence it is able to separate them better. Okay, so you can see the difference. So this is an RBF kernel trick, which makes it really, really faster with so many similarity features. Okay. Now, there are a few more things you need to take a look at. When we increase gamma, it makes the bell curve narrower. Okay. Right. So RBF is again a kernel trick. Okay. It's a basically internal algorithm optimization. Okay, that we will actually talk about the kernel tricks after this. After this, we'll talk about the kernel tricks. Okay, so RBF or the previous kernel trick we'll talk about after this. Okay, towards the end. The two parts were understanding how does an algorithm work, how does SVC, the support vector work, and the kernel tricks. We'll talk about it towards the end. Okay. Now, so let's take a look at the impact. Okay, when we increase the gamma, it makes the bell curve narrower. Okay, it makes the bell curve narrower. Okay, what does it mean? The bell curve is becoming narrower. Okay, so even here, if you see, if the gamma is increasing, the bell curve, instead of being like wider, it is becoming narrower. Why? Why? Because as you increase gamma, the influence of each parameter, the deviation of the distance in each parameter becomes more emphasized. Okay, so it starts considering the tiny differences to be big differences, and therefore increasing gamma actually increases the similarity, and hence the curve is narrower. Okay, so okay, so also with increasing the gamma, the decision boundary, you can see like here the decision boundary here, you can see it has become irregular. Okay, instead of being smoother, earlier it was quite smooth, now it's kind of deviating. Okay, and right, so while the smaller gamma makes the bell curve wider, you can see between these, if you compare these two, the bell curve is wider. Second is instances have a large range of influence. Okay, so each instance is more influential in this case. Now, okay, so decision boundary is kind of smoother. Here it's not smoother. All right, so you can see that the similarity features actually are kind of overfitting everything. It's trying to memorize everything. So, but in complex structures, the similarity functions can actually solve a lot of problems. Okay. A question from Bintao: could we also calculate precision recall with matrix confusion function here? Yes, we can definitely do that in the same way, the way we have learned earlier. Okay. Okay. So these are the few things we did today. First, we did the first kernel trick with polynomial features. Okay. And then we did the Gaussian RBF kernel. And there are many other kernels as well. And you should always do the cross validation and do the grid search. Okay. So the linear kernel, in every situation, the linear kernel is faster for larger data set. Okay. Okay, but SVC, so the SVC one is little more slower as compared to this. Okay, but the precision of SVC is higher than the linear kernel, and therefore that is the impact. All right, so good. Okay, a question from Bintao is, can we also calculate recall precision with matrix confusion here? Remember our yesterday's discussion? Who will like to do it today? Kamal? In this case, what we have is what we have is X and Y. Okay, I think you should try. And when we say fit here, okay, we are generating that. One thing you could do is, okay, this is going to be horrible actually, because the data is what should I say? Data is random actually. Okay, since data is random, the chances of it having a certain pattern is going to be bad. But nevertheless, we must give it a try. Okay, so let's say we have generated, okay. Is anybody giving a try with me? Okay, I'm just naming it this. All right. So let me also open the classification one. That will be helpful for all. Okay, so these are X-all and Y-all. So what we could do is we could, okay, so what was that? What are we trying to achieve? We are trying to basically do the cross-validation. Okay, so let's just say split data first of all. Okay, so we have X, we'll just call it X-all, Y-all, and X and Y. Okay, so we have say thousand, not thousand will be too much. We'll just take say 100, and from the beginning till 50 and 50, 50 and 50. Okay, so what we are doing here is, so X equals from the beginning till 100, not really like this. We'll just say 100 here. All right. Okay, so this remains as such. Now, what we do is we'll just take a look at Xtest. Oh, it's empty. Wow, this is still empty. Yeah, this is good enough. Then we have Y-test. All right, so what we can do is we can, whatever we have generated just now, polynomial kernel, and we are saying, okay, so then we're going to use predict. All right, so I think this is good enough. We're going to say polynomial kernel dot predict. Okay, So we are saying, what was that? Cross. Okay. Confusion matrix and the actual versus predict. So are we doing good? So we'll say y underscore test. Let me just import confusion matrix. Okay, so not bad actually. Yeah. Okay. So this one is having this kind of situation, and then if we say, okay, now you can see there is okay. So what we have here is we have polynomial 101. This, what is the difference between the two? There is one this and there is one this. Okay, so we have this one is with kernel equals poly, and their degree is 3. Here degree is 10. Okay, so you can see that all right, coefficient is 100 and so on. All right, so you can see that degree 3 is doing a better job than degree 3 is doing the better job than degree 10. Okay, all right, all right. So here is good. So, but honestly, it wouldn't be much of a significance. All right. Okay. A question is what is diamond and what is the square? So I think one is 0 and one is 1. And let me just see. Okay. So here, basically, if you see, the normal one has got better accuracy. You can see in both the cases, the the true positive and false negative are both maximum in case of this and bad in this case. All right. Who else is able to do it? Okay. Yes. Go ahead, Kamal. So basically, you have to import this. From matrix, a package of sklearn, you have to import confusion matrix. There is no better way than that, actually. Okay. Yeah. I'm not sure if we could do search help Python from Jupyter. Is there some kind of a plugin or something? If there is some plugin, then I would love to use that. I think I'll take a look at it. It could have been great if you could just search for confusion matrix and it could suggest that it is there in a particular package. Yeah. So that's the deal about most of the strongly typed languages. In most of the strongly typed languages, it's easier to give the list of functions because the data type is static and the editor or the compiler just looking at the code without running the code, the editor can figure out the data type, right? But in case of Python, without running the code, editor can't really figure out the data type. Okay, so one more thing, let me just try this. Does it help? So if I say from a scalar matrix, okay, import, import. Oh, it seems to work. You can press tab. Okay, you could press tab. Okay, so you could take a look at from sklearn dot this. So you can see there are so many of them. Okay. But it could have been cool if there was some kind of a search function and we could just search for the keyword and it could show us. Okay. I remember there was this tool on you know to sklearn documentation search. So what it did was there was this nice tool which would basically download all the manual, keep it local, and it will let you quickly search. Okay, it would let you quickly search. Okay, so let me just see if there is a way to provide. There should be a simple kind of, like you have a desktop search. There should have been a similar one, and that could actually help us. All right, that's a cool idea. That's a cool idea. Good, good. So now let's continue. So how many of you were able to do the cross validation, the confusion matrix? Okay, in support virtual machine. Was anybody else able to do it? Balaji, Vinta, Gigi, Kamal, Noor, Pavan, and Ross? Okay, wonderful, wonderful. All right, so let's continue our discussion. All right, so so we talked about a couple of algorithms. We talked about linear SVC. We also talked about SVC. So the general thumb rule is we start with linear SVC. It's based on something called a lib. The internals differ from each other. Okay. So linear SVC is based on lib linear library, some other library, and it scales linearly with number of instances and number of features. Okay. It does not support kernel tricks. Okay, the time complexity is m into n. If you have m number of features and n number of data set, the time complexity, which is number of the time taken to do the computation will be proportional to the number of features multiplied with the number of instances. Okay. Now, the SVC class is based on something called libsvm library. This class supports the kernel tricks, and the time complexity is little more than linear SVC. Okay, kernel tricks are powerful. They help you achieve better results. Okay, with less complexity. So the only downside of the SVC class, though SVC class supports kernel tricks, the time complexity of SVC class is m square into n and m cube into n. Okay, which is horrible if m is bigger. So if m is bigger, or so if m is bigger or n is bigger, it's going to have huge impact on the overall performance. It's perfect for complex but small or medium training sets. Okay, if you have a small training set and it's really complex, then SVC class could help. But if you have a little bigger data set, use the linear SVC. This is far better. All right. Okay, question from Noor is, can you expand on time complexity? Okay, let me give you a very simple example. Okay, let me give you a simple example. Let's say we have var equals x, okay, and we are saying for I in x, okay, and okay, let me just say this, range x, and we have x equals 10, okay, or okay, so x equals 10, and okay, or let me just put it in this way. Okay, this is the important part. So, and interestingly, in most of my as opposed to the common hypothesis, most of the data science interviews, they mostly asked me about the time complexity. That was my first round of interviews. Okay, and yes, I was being interviewed before Amazon with somebody, and they asked as part of my machine learning interview, they asked me a couple of things. They asked me to do the implementation of solving n consecutive equations, and then they kind of try to understand whether I understand the time complexity or not. Okay, so let me just give you a quick refresher. Probably that would help. Okay, so we could say print I. Okay, so or let me just do print I into 3. Okay, so my question here to you all is, what is the complexity of this algorithm in terms of the records here? This is our data set, X is our data set. What is the complexity? Complexity is how our time is going to vary with the data set. If it has n records, how many records are going to be here? How many times the print statement is going to be called? N times, right? Therefore, our overall time complexity is O(n). Okay, right? Make sense? This is called O(n) complexity. Yes, we'll call it big O. All right. And we always kind of compute the average time. Okay, there are average average time, the worst case scenario time, and the okay. So those are the two metrics that we generally carry. And since it's impossible to carry exact time, so instead of computing exact time, what we compute is, or what we track is, what is the relationship between data set and the time it's going to take. Okay, or number of steps versus the input records. N means input records. Okay, On means order of n. Okay, so the number of print statements are going to be of the order of n. Okay, so yeah, sometimes we take care of the average one, worst case. So all right, so either one is fine, but the important part is we must take care of the order. All right, good. Now, next one is, there is big O. Big O is for worst case. Small o is for the stage ohm, which is for the average one, and so on. Okay, so now where did it go? Here. All right, now let me quickly ask you this. So, okay, now here, let's say we have for I in X, okay, and we are saying for J in X, okay, if I equals j, then print I into j. Now, what's the complexity of this one? Okay, yeah, we'll just keep a track of the worst case scenario. Okay, complexity means if, in what way our outcome, what order our outcome is going to be impacted. If there are n number of records in X, how many times this condition will be checked? If there are n records in X, okay, so for each of n, the second loop is going to be executed, which again will have n number of steps. So effectively, it is going to be n. Okay, so we could just say counter equals 0, and we could say counter plus equals 1, and say print counter. Okay, okay, so let me just also put here. Okay, so let me just show you. So you can see that, so there are 5 records in the input, and counter's value is 25. Okay, therefore it is going to be square. Had there been 6 here, then the total counter would have gone by 36. Okay, is it clear to everyone? So therefore, this is order of n square. Okay, meaning if as the data grows, how many steps, how our number of steps going to grow. Okay, if data becomes 5, from 5 to 6, the steps are going to be 36. Okay, so all right, does it make sense to you? So similarly, if we had, say, further more complex system, and we had say one more loop here, and okay, this, then had there been 3 loops instead of 2, what would be the complexity? n cube. Wonderful. Now let me ask you a few trick questions. Okay. For I in x, okay, I equals, okay. Uh, so let me say I equals 1000. Okay, we'll say while I greater than 0, I equals I by 2. Okay, what's the complexity of this one? Anybody? Okay, okay, let me just, okay, so, all right, this is something that is going to give you an idea. Okay, I'm just wondering what happened here. What happened here? I have no clue. So initially I is 10. Am I doing something wrong here? Yeah, I will be always positive. No, but I equals, oh, this is doing the integer part. Okay, so yeah, I was expecting it to be integer division, and I keep forgetting that I'm in Python 3. So, right. Okay, so you can see that it is basically log of, the complexity of this one is in terms of log. Okay, so you'll see that even when there are so many zeros, it's actually going by 20. Okay, so the complexity is log of ln of n. Okay, so yes. So whatever is our input number, it's a log of that one. So the complexity is order of, we call it log of n. I'll explain, because every time data is being halved, correct? Every time data is being halved, and when such kind of scenario arises, it's a GP, I mean the geometric progression, and in such case, the overall complexity is always half. Okay, say for example, when we are looking for a data using a binary search in a list. Binary search is how does binary search work? If we have list of numbers which are increasing in number, which are increasing in order. So what we do is we pick the middle point. Let's say we have a list of numbers which are ordered, and we are looking for a particular number in this ordered list of numbers. Okay, the way we are going to search is we are going to go to the middle of this list and check if the number that is existing in the middle is lesser than or greater than the number that we are looking for. And if it is lesser, if the list contains smaller number. So that means we don't have to look for our number in the first half of the list. So we ignore the first half of the list and we only retain the second half. If the number that is found in the middle of the list is bigger than the number that we're looking for, that means our number would exist in the first half, so we ignore the second half. And we continue to do the same process again and again on the remaining list. Okay, and that way we are essentially cutting down the list by half in every step. So in scenarios like this, the complexity is logarithm of n. Okay, you were right the first time. Okay, so a very good question from Noor. If had it been I by 3 here, then what would have been the logarithms? Then it'll be the complexity would have been log 3. 3 is the base of n. Okay. All right. All right. So that's what happens here, that every time the data is halved uh, or something like that. All right. So this is where the logarithm comes into play and is quite useful in doing the computation. And you'll be amazed to know this. Let me ask you this question. So here, let me show you. Imagine that in your database, there were 1,000 records. Okay. And it was taking 10 seconds. All right. Imagine that you have a database table which is indexed. Okay, which is indexed. It has 1,000 records and say it is taking 10 seconds. It is taking 10 seconds. Now, what will happen if it has these many records? How much time will it take? Anybody? See, when there were 1,000 records, let's say it was taking 10 seconds. Okay, so 10 seconds for 1,000 records. Okay, now when I'm increasing the number of records, okay, how many seconds for this? How many seconds for these many? Okay, you'll see this thing. It's actually 27 seconds. Okay, I'm just taking an assumption that okay, the generally time taken is proportional to the computation. Yeah. So you can see that the difference. So when you index the database, this is the kind of performance boost you generally get, okay? Because when you have a database index, the database index are mostly kind of a binary search, and hence, when you look up something, they become incredibly fast, okay? So you can see that for 1,000, it was taking 10 seconds, and for these many records, it might take 27 seconds, all right? I'm just, making it a little more exaggerated, but the truth is the proportional is something that is important. Proportional is something that is important. If it took 10 seconds for 1,000 record, it'll take 27 seconds for these many records. That's the power of binary search. Okay. All right. So correct. It's approximately 3 times. Okay. So log n is 10 base. This is 2 base. Okay, this is 2 base. All right. When you use the calculator, and do you see my desktop? So let me just show you. Okay. So does it have log 2 base? Okay, it doesn't have log two base. All right. So here we're talking about the log two base. All right. So this is how it is going to be. All right. So basically the idea behind and these are the very standard questions people ask. And yes, the second question that was asked is what happens in case you change it to 3. It's an important question. Keep in mind, you just have to say that it's log 3. Okay. All right. And if you had, say, another logic here, I'll just copy paste another just to keep it with here. So if we had something like this, now the complexity is going to be okay. All right. So it's kind of going to be square root. I think so. Okay. Just think over it. Just think over it. We can discuss it later. All right. So we'll continue our SVM discussion. The next Saturday is going to be I'm going to be in Singapore. If any of you is in Singapore, feel free to come over and meet. And next Sunday we'll have the class. Okay. Sunday for me. Okay. Next Saturday, I'll be in Singapore. All right. Thank you, everyone. I look forward to see you next Sunday. Sure. I will commit. Okay. I'll commit. I'm hoping that it would work. Okay, so support vector machine is something I'm going to commit, not the training models. Okay. Or should I commit both? Changes during the session. Confusion matrix plus Baker. Okay. What did I do? Get the status. And did I? Okay, let me just check if my changes are there. They're supposed to be there. No. Okay, good. this is detached from, okay, I'll have to just create a label here, git checkout master. Okay, it says that give a branch name, git branch, let's say, actually the last time what we had done was we had, okay, so we'll say git merge. All right, so you might have to say this in your, in case you have, and then git checkout. Okay, you can say git checkout master, because last time, remember, we had checked out a particular version, because of which we went into a separate branch, and that's where we were working. So, all right, so that's why it wasn't committing. All right, wonderful, wonderful to have all of you in the session. I look forward to see you next week. Great. Thank you, everyone. Have a good time.